Question 1. An object of mass m rests on a horizontal plane. The angle that plane makes with the horizontal is slowly increased from 0. Okay, so it goes like this. When theta equals theta naught, the object begins to slide. What are the coefficient of friction mu on S and the normal reaction force N of the plane at theta equals theta naught? Let's look at some forces. The weight of this object is mg. The component of force down the slope is mg sine theta. The component of force perpendicular to the slope is mg cos theta. Oh, right, that's the normal force, isn't it? So the normal force, reaction force, is mg cos theta. So it's not B or C, it's A or D. Let's look at the coefficient of static friction. There's a formula in the data booklet that looks like this. And we can rearrange that for mu on S over N. We know that N is equal to mg cos theta. We've just worked that out. Not, of course. And the force of friction, at the moment it started to slide, the force of friction will be the same as the force down the slope. So we can have mg sine theta up here. These cancel. Sine theta over cos theta is equal to tan theta naught. So our answer is this. So the answer is D. Question 2. A spring of negligible mass and length L naught hangs from a fixed point. When a mass is attached to the free end of the spring, the length of the spring increases to L. So that becomes L. The tension in the spring is equal to Kx. So tension is equal to K delta X, where K is a constant and delta X is the extension of the spring. What is K? Okay, well, this mass that's attached to the spring, that mass has a weight, and that weight is mg, and that's causing the tension in the spring. So instead of writing tension, we write mg. K is the spring constant, and delta X is the extension in the spring. But in this situation, the extension in the spring is L minus L naught, because that's the difference here in length. So instead of writing delta X, we write L minus L naught. Rearrange that for K. So K equals mg over L minus L naught, and the answer is C. Question 3. A ball with mass m moves horizontally with speed u. The ball hits a vertical wall and rebounds in the opposite direction with a speed v is less than u. The duration of the collision is t. So as it hits the wall, it's in contact for t. What are the magnitude of the average force exerted by the wall and the loss of kinetic energy? Can I give you a massive hint? Every time you see the word average force, you are dealing with impulse. It's the only time, really, in physics that you see the word average force. So let's write down the equation for impulse. F delta t equals m delta v. We know that delta t in this case is equal to big T. I'm looking for average force. So F t equals m delta v. Our delta v, now we need to be careful here because we've got to choose a direction as positive. So let's choose right as positive and left as negative. Change in velocity is the final velocity minus the initial velocity. Final velocity is going to the left, so it's negative, minus the initial velocity, that's positive. Okay, so F is equal to m, let's take that minus out there, v plus u over t. And really that minus just means what the direction the force is in. So the magnitude, and that's what we're looking at, magnitude of the average force is equal to mv plus u over t. So it's either A or B, it's not C or D. Then we're looking at the loss of kinetic energy. The loss of kinetic energy is the kinetic energy before minus the kinetic energy after. So it's a half mu squared minus a half mv squared. We can take the half and the m out, and we have u squared minus v squared. That is not the same as u minus v all squared, which is they've tried to fob us off with here. Okay, so the answer is A, because that's the loss of kinetic energy and that's the average force. Question 4. A company designs a spring system for loading ice blocks onto a truck. The ice block is placed in a holder H in front of the spring, and an electric motor compresses the spring by pushing H to the left. When the spring is released, the ice block is accelerated towards ramp A, B, C. When the spring is fully decompressed, the ice block loses contact with the spring at A. The mass of the ice block is 55 kilograms. Assume the surface of the ramp is frictionless, that's important, and that the masses of the springs and the holder are negligible compared to the mass of the ice block. Describe the motion of the block. Oh, another banger of a tip here. When you see the words describe the motion in an exam, in a physics exam, obviously, you really want to use one of 4 different phrases. You want to use the word stationary, constant velocity, accelerate, or decelerate. So we're going to use one of those 4 phrases in each of these questions because we've seen the phrase describe the motion. Okay, so we want to describe the motion from A to B with reference to Newton's first law. Okay, well, Newton's first law is that an object will remain at rest or travel at a constant velocity unless acted upon by an external force. Let's now actually look at point A. The forces acting on the block at that point are the weight and the reaction force. There is no thrust force or push force. There is no friction force because it's frictionless. So there's no forces acting on it in a horizontal direction. The forces are balanced. If we then go to the answer, we'll say the forces are balanced. There is no push or friction force. And then we've got to come up with one of these 4 phrases. The block travels with constant velocity. Number 2. Let's have a look at the block on the slope. The slope has a force acting down it of mg sine theta. The surface is frictionless, so there's no friction to add in here. Forces this way are balanced. So there is an unbalanced force, but it's acting down the hill. With that in mind, there is an unbalanced force acting down the slope. And you could even say of mg sine theta. This will cause the block to decelerate. And you can see we've used the phrases constant velocity and decelerate. My biggest tip is, if you see the word describe the motion, use one of those 4 phrases. Question 5. A boy jumps from a wall 3 meters high. What is an estimate of the change in momentum of the boy as he lands without rebounding? So we have this boy, he lands here. Before he lands, he has a momentum mv, and after he lands, he has a momentum 0 because he's not got any speed. Okay, so the change in momentum is equal to the final momentum minus the initial momentum, and the final momentum is 0. So what we're really looking for is the momentum here just before he hits the ground. To do that, we need his mass and we need his velocity. Now this is where it's going to feel very uncomfortable for a lot of students, because you're having to make lots of estimates. Now, I am a fully grown woman. I'm around about 65 kilograms. So I'm going to say a boy, let's just say his mass is around about 50 kilograms. It's an estimate, doesn't matter. Now we need to estimate what his velocity is, and the only information we have is he's free falling due to gravity from a height of 3 meters. So we can use the Suvat equations to find out what his velocity might be as he hits the ground. We know that S is 3. His initial speed when he leaves those 3 meters is 0. We want to find out what V is, and the acceleration is 10. Using this information, we can use V squared equals U squared plus 2AS. U is 0, so V squared equals 2 times 10 times 3. So V squared is equal to 60. Okay, let's say, let's make it easier. Because we're estimating, we're just looking for an order of magnitude. Let's make it 64, and that means that V is equal to 8. All right, so the momentum just before it hits the ground, P equals mv is equal to 50 times 8, which is 450 kilograms meters per second. We're looking at 5, so let's round that up. So it's 500 kilograms meters per second is his change in momentum, which is equal to 5 times 10 to the 2 kilogram meters per second. So our answer is C. I know a lot of people will feel uncomfortable with that. We made so many estimations, but really look at the answers. It's not going to be 5 kilogram meters per second. It's not going to be 10 to the 3 kilogram meters per second. So really we're looking between B and C. And those estimates that we've made there would be enough to always get us the magnitude of this. When it says estimate, just do your best. Use your knowledge, trust your common sense, and I'm sure you'll get there. Question 6. A mass is suspended from the ceiling of a train carriage by a string. The string makes an angle theta with the vertical when the train is accelerating along a straight horizontal track. What is the acceleration of a train? By looking at this diagram, we can assume that the train is accelerating in that direction. And we know that because if you imagine yourself on a train and it suddenly accelerates, you fall backwards due to Newton's first law. So what's happening to that mass at that point is that the mass is feeling a force that way of F equals ma, because that's the force that's causing the acceleration. This mass also has a weight of mg, and it has a tension in the string of T. And at that point, the mass is stationary relative to inside the train carriage. So it means that these three forces of tension, weight, and the accelerating force, ma, are all in equilibrium. And we can draw this triangle to show that. And we know that this is theta. We want to find out what A is. And we really have no concept of T. That's not mentioned. Tension is not mentioned. So what we can do is we can use the trigonometric function and say tan theta is equal to opposite A over adjacent G. The two m's cancel. And if we rearrange for A equals G tan theta. And the answer is C. Question 7. A ball of mass m strikes a vertical wall with a speed v at an angle of theta to the wall. The ball rebounds at the same speed and angle. What is the change in magnitude of the momentum of the ball? Right. Change in momentum is equal to the final momentum minus the initial momentum. And momentum is a vector. Wait a minute, we can turn these into momentum vectors. P equals mv, and that's pi, that's the initial momentum. P final is equal to mv, and that's the final momentum. Do you remember in A1 kinematics, I taught you the little trick about how to subtract vectors? What you do is you say final momentum plus minus the initial momentum. What that means is we have to put the initial momentum vector in the opposite direction and then add the two together. So we have final momentum, tip to tail with minus initial momentum. And the change in momentum is the resultant vector between these two. This is getting a bit easier because all we have to do now is recognise that these are two right angled triangles. That angle is theta. We can use trigonometry to find out what this length is, and it's just double it for this whole delta p. So this length here, we have, it's the adjacent to the angle, so it's cos theta equals the adjacent value over the hypotenuse, and we want to find out what the adjacent value is. So A is equal to a half delta p, which is this length here, is equal to h cos theta, which is pi cos theta. And the other length of this is exactly the same, right? So delta p is simply 2 times that. So it's 2 times initial momentum cos theta. But because the initial momentum is actually equal in magnitude to the final momentum, then delta p is equal to 2 mv cos theta. The answer is B. Question 8. Two objects M1 and M2 approach each other along a straight line with speeds V1 and V2 as shown. The objects collide and stick together. What is the total change of linear momentum of the objects as a result of the collision? I actually feel like this might be a trick question, but let's go with it anyway. The change of linear momentum means this, and it's final momentum minus initial momentum. So the instinct is to do this and calculate the momentum before the collision and after the collision. We'll do that. So the momentum before is m1 v1, and let's make that in the positive direction, plus m2 minus v2. Okay, so the total momentum before is m1 v1 minus m2 v2, and there's minuses there because v2 is going in the opposite direction. The momentum after is m1 plus m2, and they both move off at a speed that we don't know of. We'll just call that v. So this is final momentum, this is initial momentum, and by the law of conservation of momentum, pi equals pf. So if we try and do pf minus pi, and they're equal to each other, then it's 0. The change of linear momentum as a result of this collision is 0. Question 9. We've seen the first part of this question in the Activate the Application tutorial for kinematics, but we'll go over it and answer the second part. A tennis ball is hit with a racket from a point 1.5 metres above the ground. The ceiling is 8 metres above the floor. That means that this distance here is 6.5 metres. The initial velocity of the ball is 15 metres per second at 50 degrees above the horizontal. Assume that air resistance is negligible. Determine whether the ball will hit the ceiling. In A1 kinematics, we did this. We found that the maximum height of the ball would be 6.7 metres, which is higher than this 6.5 metres, so we came to the conclusion that yes, it would hit the ceiling. Now we're getting into the force and A2 material. The tennis ball was stationary before being hit, so the initial speed is 0. It has a mass of 5.8 times 10 to the minus 2 kilograms and was in contact with the racket for 23 milliseconds. Calculate the mean force. Do you remember my exam tip? If you see the word average force or mean force, you're looking at impulse. Okay, so we've got to get the impulse formula out. I'm going to do it up here, just in the interest of space. So the mean force times time equals m delta v. We want to find out what mean force is. So it's m delta v over delta t. The mass is 5.8 times 10 to the minus 2 times the change in velocity. The final velocity is 15. The initial velocity, it was stationary before, so it's 0. And the time it's in contact was 23 milliseconds, 10 to the minus 3. So our answer is 37.8 newtons. And all the data is given to 2 significant figures, so you round that to 2 significant figures, 38 newtons. B2. Explain how Newton's third law applies when the racket hits the tennis ball. Do you remember those rules for a Newton's third law pair. So we meet all the criteria for a Newton's third law pair. But the question says explain how third law applies when the racket hits the tennis ball. And here's how I would write that. I would write the racket exerts a force on the ball. The ball exerts an equal and opposite force on the racket. Now, if you can remember that sentence off by heart and just change these 4 words, you'll always get the full marks, 2 marks, because what this sentence does is it takes all of these rules for a Newton's third law pair and it puts it into one sentence. So whenever you're asked to do Newton's third law, I would suggest you use this sentence as a template and just input the 2 different objects in this sentence as long as they all meet the criteria for the Newton's third law pair. Question 10. Curling is a game played on a horizontal ice surface. Here's a bit of interesting knowledge about curling. Scotland is actually really good at curling. We have boasted many of the world championships in curling. Amongst the many brilliant things in Scotland, curling is one of them for us. Okay, back to the question. A player pushes a large, smooth stone across the ice for several seconds and then releases it. The stone moves until friction brings it to rest. The graph shows the variation of speed of the stone with time. So we can see that the maximum speed is here. The total distance travelled by the stone in 17.5 seconds is 29.8 metres. I will tell you the area of this large triangle underneath here is equal to the distance travelled, and that is 29.8 metres. So the area of that large space is 29.8 metres. What the first question asks is determine the maximum speed v of the stone. We want to find out what this value is here, and that is this line here. We want to find out the length of that line. We can do that by recognising that the area of this triangle here is a half base times height, and the area of that triangle there is a half base times height. And the total area of the two of those is equal to 29.8. So I'm going to start my working out up here. Area of, let's call that triangle A, and that's triangle B, is, so the area of triangle A is a half times 3.5 times this length here, and we don't know the value of that, so let's call it y, plus the area of B, so that's A. The area of B is a half times the length, which is 14, times the height again is y, and all that equals 29.8 metres. I'm going to go back to blue so it's nicer for your eyes. I always think red is very aggressive. Okay, so 1.75y plus 7y is equal to 29.8. That means that 8.75y equals 29.8. So y is equal to 3.41, and that is a speed meters per second. So our Vmax is equal to 3.41 meters per second. It's okay to leave it in 3 significant figures. Yep, well, the data is in 3 significant figures, so that's fine. B, determine the coefficient of dynamic friction, which is that, between the stone and the ice during the last 14 seconds of the stone's motion. During the last 14 seconds, we know that it is decelerating. And it's decelerating, I'm going to do my working up here. It's decelerating due to the force of friction. And that force of friction is causing a deceleration. And we can use F equals ma to find the value of that deceleration. But actually, we don't want to find the value of the deceleration. We want to find the value of mu on d. But we know from our data booklet that the force of friction can be given the formula mu on d n equals ma. Okay, and we know that n is the normal or the reaction force, and that reaction force if we think about the stone on the ice, that reaction force will be mg. Down the way is weight, and the reaction force up the way is mg as well, because it's equal and opposite. So actually what we've got is mu on d mg, if you want you can make it minus because it's in the opposite direction, equals ma. The m's can cancel. We're nearly there. We want to find out what mu on d is. A over g. What's A? What's the... Oh, we can find the deceleration of the stone. I'll do it over here. Up here for your attention, please. A is equal to V minus U over T. The final speed is 0. The initial speed is 3.41. The time taken to do that is 14. So the deceleration of the stone is 2.43 meters per second squared. We're going to take this all the way back. And we're going to put in here minus 2.43 divided by 9.81 gives us a value of 0.025 minus, and our answer there becomes minus mu on d equals minus 0.025. Minuses cancel. So our value for the dynamic friction is 0.025. It's a dimensionless number. It doesn't have any units. That's our answer. Moving on to C. The diagram shows the stone during its motion after release. That means when it's decelerating. Label the diagram to show the forces acting on the stone. Your answer should include the name, the direction and point of application of each force. We've kind of done that already. From the centre of gravity, we'll have a force going down the way, which is weight. The reaction force is equal and opposite to that, and that's given the reaction force here. And then of course there's the frictional force, and after it's been released, nothing's pushing it forward, so we've got the frictional force acting upon it here, and that friction happens between where the object is and what it's touching. So the frictional force comes from point here. The key here is to recognise that the length of the weight vector should be equal to the length of the reaction force vector, and the point of application of the reaction force vector should be perpendicular to the surface. The weight vector should be from the centre of mass, and the force of friction vector should be between the two surfaces. Question 11. An elevator and its load have a total mass of 750 kilograms and it accelerates vertically downwards at 2 meters per second squared. What is the tension in the elevator cable? If you struggle with following my working out for this, I highly recommend the extra tutorial I've done for you on elevators. You'll find it as part of this topic. It's very easy for you to find the tutorial. I've done a separate tutorial on elevators. You're more than welcome to go and find it. But what I will say is, since the elevator is accelerating downwards, the tension in the cable is less than the weight. All right, so that means that weight minus tension is equal to MA. Okay, so weight is equal to 750 times 10 minus T equals 750 times the acceleration. So we have 7,500 minus T equals 1,500. So 7,500, let's swap these two around, minus 1,500 equals T, so T equals 6,000 newtons, which is 6 kilonewtons. The answer is B. Let me give you the final plug for my extra tutorials on elevators as part of A2 Forces. Go and have an explore, you'll find it, I promise. Question 12. An inelastic collision occurs between two bodies in the absence of external forces. Okay. What must be true about the total momentum of the two bodies and the total kinetic energy of the two bodies? This is easy. An inelastic collision means that kinetic energy is lost. So kinetic energy is not conserved. Can we get rid of any things here? Okay, kinetic energy is conserved. That's not true. Kinetic energy is not true. So it's not B or C. The law of conservation of momentum tells us that in the absence of external forces, total momentum is always conserved. So we want to go to the answer where momentum is conserved, which is A, but that says momentum is not conserved, so it's not D. The answer is A. Question 13. A horizontal disc rotates uniformly at a constant angular velocity about a central axis normal to the plane of the disc. Point X is a distance 2L from the centre of the disc. Point Y is a distance L from the centre of the disc. Point Y has a linear speed V and a centripetal acceleration A. What is the linear speed and centripetal acceleration of point X? Well, let's look at the linear speed first. Let's deal with Y as our starting point. V, Y, is equal to 2 pi r over t, which is 2 pi L over t. Easy enough. Now let's look at Vx. Vx is equal to 2 pi r over t also, but the radius is doubled, so 2 pi 2L over t. So it's 4 pi L over t, which is equal to 2 times Vy. So our linear speed of x is equal to 2v. Now let's look at the acceleration. The acceleration of y, that's equal to Vy squared over L. Now let's look at the acceleration of x. It's equal to v squared over r, but we know that it's already 2Vy squared over 2L, which is 4Vy squared over 2L, which is 2Vy squared over L. And you can see that that's 2 times that. So the acceleration of x is equal to 2 times the acceleration of y, which is 2a. So the answer is B. Question 14. The diagram below shows part of a downhill ski course which starts at point A, 50 metres above the level ground. Point B is 20 metres above the level ground. At the side of the course, flexible safety nets are used. Another skier of mass 76 kilograms falls normally into the safety net with a speed of 9.6 metres per second. Calculate the impulse required from the net to stop the skier and state an appropriate unit for your answer. We'll do this up here. We're looking for impulse. J equals F delta T equals M delta V. We don't have that information, but we do have the mass of the skier, which is 76, and we do have the change in speed because we know they're going to go from 9.6 metres per second down to 0, so 9.6. So our answer there is 729.6 Newton seconds. I think the most amount of significant figures given in this question is 2 significant figures. Let's bring it down to 2 significant figures, 730 Newton seconds. We could also have used the units kilograms meters per second as well. Either of those 2 units are fine. Number 2, explain with reference to change in momentum why a flexible safety net is less likely to harm the skier than a rigid barrier. The change in momentum is equal to F delta T. And this value of change in momentum is a constant at 730 Newton seconds. That can't change. But what can change is how long it takes to make that change in momentum. If we increase the time it takes for the change in momentum to occur, that decreases this average force felt by the skier. And a smaller force means less harm. So we want to write that down by introducing a flexible safety net. The time taken to stop increases. Given that the change in momentum is a constant, this means the average force on the skier is decreased, causing less harm. Now, I am very glad that I am not writing my IB physics exams in handwriting, because my handwriting is appalling. That is because I haven't really written in the last 20 years. I've only typed. And you being at school will write a lot more than I do. So hopefully your handwriting will be absolutely perfect and not as bad as mine.
I've had a few people write in and they're struggling with question 20. So let's go through it. The first thing I'd like to note about question 20 is it takes in material from A2 Forces of Momentum, but it also takes in material from D1 gravitational fields. So if you haven't studied D1 gravitational fields, you're going to find this very tricky. The other point to make about this question is this is one of the classic, very difficult multiple choice questions. 50% of your multiple choice questions will require multi-step calculations. That means you'll have to undertake more than one calculation to get the right answer. And this is one of them, so it's great for us to practice it. Let's go. Satellite X orbits a planet with orbital radius r. Satellite Y orbits the same planet with orbital radius 2r. Satellites X and Y have the same mass. What is the ratio of the centripetal acceleration of X over the centripetal acceleration of Y? So we want to have this ratio here. We know that AX, very simply from our data booklet, is VX squared over R. And we know that AY is VY squared over 2R. And if you can pop that into here, that will be Vx squared over R. And then AY on the bottom, so Vy squared over 2R. That doesn't work, does it? So let's take them out. And that has to go up to the top. 2R. We can cancel out the R's. So we know that 2Vx squared over Vy squared is the ratio that we're looking for. But we don't know what Vx and Vy is. That's our first calculation. This is a multi-step calculation, so we have to do a second calculation to find out an expression for Vx squared, an expression for Vy squared. Now, I know we're dealing with gravitational fields, we're dealing with planets and satellites and things orbiting around each other, so we can definitely use Newton's law of gravitation, which is G m over r squared. Let's look at for X. We have G, that's the mass of the planet, m is the mass of X, over r squared. Still doesn't give us a value for V though. However, we know that when a satellite or a planet is in orbit, the gravitational field, due to Newton's gravitational law, is equal to the centripetal field force. So we can say G mx over r squared is equal to mx vx squared over r. Can you see that's the vx squared term we want there? So cancel out the m's, cancel out one of these r's, and we have a term for vx squared, which is g m over r. So we can pop that up into our equation in a moment. But we also need one for y. So we do the same. G m my over 2r all squared equals my vy all squared over 2. Okay, let's cancel out these. That's going to be g m over 4r squared equals vy squared over 2r. Take one of them out, and that's going to give us vy squared equals g m over 2r. So we're going to take this and substitute them up here and here. Let's do that in green. So we have 2vx squared, which is g m over r. And then vy squared is g m over 2r, but that goes up to the top, so 2r. I'm going to cancel some stuff out. That cancels with that, that cancels with that, that cancels with that. And we have the answer is 2 times 2, which is 4. The answer here is 4. That was a lot of work. And it's one of these questions that will demand a lot of work in your exam. but 50% of the other questions will be relatively quick to answer. So you have to sort of try to balance that out when you're looking at something as difficult as this. Hope this helped. Bye.